times, I think let me still go ahead. Still have 7 minutes, right? So let's start to talk about the Pauli matrices, right? Pauli matrices actually refer to these three matrices. Sigma C equals to 1, 0, 0, negative 1. Sigma Y equals to 0, negative I, 0. And sigma X equals to 0, 1, 1, 0, 1. Okay? These are Pauli matrices. Okay? That's it. Memorize it. Now, but however, we want to talk about some of the important property of them. One, they are Hermitian. What does it mean? Sigma I equals to sigma I dagger. Now, this I means what? I can be equals to, you need to be familiar with this notation, X, Y, C. Just pick one of them. They are Hermitian. Okay? So we already discussed what is Hermitian. Another thing is sigma I squared, which is equal to sigma I times sigma I equals to the identity matrix. This is like the Hadamard gate, right? They are that the square equals to the identity matrix. Okay, you can prove it. I will save time. I don't want to prove it. Okay. The final thing is the trace of all this matrix is 0. That's why they are called traceless. Is trace. Do you remember? The trace of a matrix, right? If I have a matrix, the trace is the summation of the diagonal elements. Just sum over them. That is the trace, right? For example, trace of sigma X equals to 0 plus 0, right? Trace of sigma Z equals to 1 minus 1, also 0. They are all traceless. Okay, this is an important property. Then finally, I want to say one thing. With the identity gate, sigma X, sigma Y, sigma Z, okay, they form the basis states or a vector. You can call them vector, although they are matrices, but they are still they are still a linear space. But now maybe I should not call it vector, but I don't know, maybe basis elements or something, right? They form the basis of the linear space of 2 by 2 matrix. Of 2 by 2 matrix. So what does it mean, right? What does it mean, right? Let me see. I covered this. Okay. Let me maybe. What does it mean? Let me just maybe write here, right? It means that for any matrix, let me just say next page. Any matrix M equals to M11, M12, M21, M22. This is a 2 by 2 matrix. It can represent it as A0 times I plus AX times sigma X plus AY times sigma Y plus AZ times sigma Z, where this A0, AX, AY, AZ are just numbers. They can be complex numbers, but just numbers. And these are the matrix. Just think about that, right? For a vector space in the past, we thought, oh, a vector is a linear combination of bases. We were talking about the vector space, that linear space, that the matrix is a linear combination of these four fundamental matrices. And I can write them as A0 times I plus a vector dot product with sigma. What does it mean? It means this A vector, I can write it as just a AX, AY, AZ, just like a vector in our real space, right? And these are numbers, so it's not in a real space, it has complex coefficient. Sigma, it is just equals to sigma X, sigma Y, sigma Z. This is a little bit funny, right? Because the coefficient in this case is the matrix, not a number. But you just do dot product. Dot product is just AX times sigma X plus AY times sigma Y plus AC times sigma Z. This is a shorthand notation to represent this, and it is very useful, right? So maybe I will just stop here. In summary, right, this is what I copied from Wiki. I hope now you will understand. All the Pauli matrices are Hermitian. We talked about that already. They are Hermitian. Together with the identity matrix, right, they form the basis for all vector space of 2 by 2 Hermitian matrices. Actually, it's not just 2 by 2, because in this case, I am only talking about a general case. Okay? How to say? Basically, what I'm trying to say is this. What I'm giving you is general. Maybe I should add one more. If M is Hermitian, which means M equal to M dagger, it turns out that A0, AX, AY, AZ are real, right? You can prove it. You can prove it. It's not difficult. Just based on this equation, plug in. You will show that these are all real. Okay? So it doesn't matter. This is just for you to appreciate this statement, right? But basically, Pauli matrix and identity matrix form the basis of the linear space of a 2 by 2 matrices. This is very important later when we talk about the density matrix. Okay, so we stop here today.
you